Thanks, everyone. All right, so this is a story with a few clarities and stuff in that most of the rest of my team has not heard. A little bit of stuff about curvature and ideas, trying to connect it to black holes and curvature, really, of space. But I want to talk about it as a story. It is very rough. It's very conceptual. And I like to think of myself as sort of in a symbiotic situation with people smarter than me. So I'm not, I was not focused enough to get advanced degrees like all of you have. And so I'm not as smart in many, many things as you. But I'm very creative. And I insist on reduction and understanding things with first principles. That I insist on. And I don't have to be very smart in any formalism for that. So I like to think of myself as modeling myself as a partnership between Maxwell and Faraday, or between Wheeler and Feynman, where Wheeler always said Feynman was much smarter than him. And Maxwell, of course, was the greatest mathematician in England at that time. And of course, Faraday had a 9th grade education. But Faraday was very creative, and he had this crazy idea that two forces that everyone believed were completely different were actually secretly the same thing. And he wrote in the only language that he had, which is English, and nobody really read it from the scientific community. And by a fluke of fate, the greatest mathematician happened to read it by practical accident, and then played around and developed Maxwell's equations, which led to many other things, right? And so look at this like a crazy story that is not fully rigorous. So that's kind of the symbiosis I'm trying to create here, with a lot of people hearing my evolving story, and it evolves. I'm usually several steps ahead of things because I don't have to calculate and do all the rigorous part. I'm free to be a scout, to go ahead of the army and scout the terrain ahead a few miles. So my story today is called Quantum Clocks and Gravity. And I want to start with our axioms here at QGR. Our first axiom is the Pythagorean theorem is true. So we have an axiom which is not provable, that theorem is true, that the proof is true, but that proof requires assumptions which are not provable within the theorem. So that specifically, by assuming the theorem to be true, we automatically assume a postulate of Euclid to be true, namely that there exists a straight line segment which can be drawn joining any 2 points. Our second axiom is the principle of efficient language. And you have to see our paper, The Code Theoretic Axiom, to get the breakdown of what that axiom is. The logic, though, goes like this. We presume that reality is made of information. And then information is meaning, including geometric meaning, which is conveyed by code or language. So we presume our information theoretic reality is dynamic and evolving. So it computes in some sense, according to some unknown code. In other words, changing relationships are fundamental. Everything is process. These processes are computational products. We observe gauge symmetries in nature, one being the principle of least action. So we deduce, we take a guess by deduction, that nature computes in the most economical way possible. And see a metric space for computer programs and the principle of computational least action by Numrich for a rigorous form of this argument. The physical code. At the limits of general relativity, quantum mechanics, and thermodynamics, things clean up a lot to reveal the golden ratio underneath it all. While the right sides of the equations are dimensionless ratio, the left sides are messy because they are full of man-made metrics. which clouds what is really going on from a first principles perspective. Marcello argues that the probability of entanglement for two electrons moving in one dimension is nature's limit of non-locality. It is the golden ratio to the -5. And then Lucine Hardy at the Perimeter Institute provided the mathematical proof correlated to experimental data for this value. So I put that down here. So today, I will build up to show you my crazy idea. And we will talk about how things get very simplified when you get out. You purify the man-made metrics from fundamental physics. And so this, of course, would be very meaningless to you at this point, but this is sort of a preview where we have these units here for these fundamental things: the Planck length, Planck time, a Planck mass, and so on. So don't worry about why that is yet. So the day before something is a breakthrough, it is a crazy idea. It is sacrilegious to other ideas that are more developed. So, the physical code again. Our foundational quasi-particle objects are quantum clocks. I define quasi-particles as coherent patterns in a dynamic system of two or more objects. So let us define a clock as a periodic pattern of change. Let us define change as two or more objects changing their relationship. And let us set this boundary and our relationship to it as our base possibility space for change. And we can change one half to red, and then the other half. And because there is periodicity in our ordered set of change, we have cycles that we can count, which is what clocks do. But the notion of change is vague and sloppy. The notion of time is not based on first principles. For some, time is the flow of change. But flow and change are imprecise. So let us convert the idea of change to the rigorous notion of ordered sets. And let us allow the order within the set to be the flow of change, such that time or change is simply the order within an ordered set. A clock is a periodically ordered set of ordered sets. So, as observers, we're accustomed to generating the flow of change via the order of our observations. In our macro-scale observations, we order the sets by our conscious and subconscious ordering of observations. An observation is always a projective transformation, giving information about the pre-transformed relationship of two or more points and the observer point. For example, I'm looking at Ahmed's head and Mike's head. And for me, they're touching, okay? But I encode that transformation is creating a triangle, which gives away, for me, information encoded in that triangle of me, the observer, right? Or the detector, if you're looking at an experiment, and particle or point A and point B. So the triangle is the projective transformation which encodes the relationship of their pre-transformed identity and my relationship to their pre-transformed identity. So the observer can be a point or a line or a surface, a volume or hypervolume. It's a projector. So you can have projectors in different dimensions. Our mathematics is that of ordered sets of projective processes or primordial observations called the AB equals P computational action. There is a game of life in this process that orders the sets according to a computational least action principle that leads naturally to complexity of self-organization, a negentropic process following directly from one of our two axioms. Think of a possibility space as an ordered set. And think of subsets of that ordered set as our state selections upon that superposition or that possibility space. So these are different state selections on one set as the possibility space set. This is an ordered set of ordered sets where all ordered sets are state selections on a single base set, the possibility space, and where the superposition of all subsets is the possibility space. So let us define a classic clock as a periodic or cyclical set of ordered sets, where the ordered sets are continuously ordered. And let us define continuous as an ordered set of two or more objects forming a series with no exceptions. So series in the mathematical sense that, right, the integers are a series. You can take them in series or out of series. The term exceptions implies that all elements of the set must be covered in each cycle. If an element is not covered in a cycle, well, it is simply not part of the clock. It's not part of the set. It's very trivial, but here is an example of the no exception concept. Because the 6 square does not change over each cycle, it is not a member of the clock set. So let us define a quantum clock as an ordered set of sets wherein the cycles of change are discontinuously ordered with no exceptions, where such order is out of series. Now, this was a periodic or cyclical ordered set, a quantum clock. At small scales of time, it appears to be without order or non-cyclical. But if I played it faster for you, it would be easy for you to notice the repeating cycles with no exceptions. The requirement for clocks to have no exceptions is key for us. I explained the logic of that. If an element does not change in a cycle, it is not part of the set defining the clock. This leads to a serious question, though. Each element of the set must change in a cycle. But does this require each element to change in its own unique frame, or can two or more elements change in a single frame or set within an ordered set of sets? Well, clearly the definition I provided you above does not explicitly prohibit more than one element from changing in a single frame. But should it, right? Because that was just my definition. To answer that, we have to go into our second axiom, the principle of efficient language. Base information as AB equals P solutions can be conserved while allowing a virtual infinite amount of higher symbolic codes and information to emerge only from the quality of order in the AB equals P ordered set. That is the ordered set of ordered sets. So what is an electron for us, this clock-based pilot wave idea? Is it emergent information or is it base information? So base information are the AB equals P solutions. They're algebraic operations on E8. If you choose not to work with projective geometry, you don't need to. You can do it all in just pure algebra, Lie algebra. It's emergent information. So our particles are emergent information. They are not AB equals P solutions. They are patterns within the ordering of two or more AB equals P solutions. The only thing that is base information, or I, we have an equation which is I, which represents a form of primordial base information, plus E, which represents all of the hierarchical strata of emergent structure in a code theoretic notion of letters, words, sentences, paragraphs, and so on. So I plus E, the sum of emergent information, equals total information, which is capital I, where total information is generally not the sum of the base information. Anyway, so the only thing that is this base information is our ordered set of objects, our AB equals P solution, defining state selections on the QSN graph, where we ignore the order. In other words, if you're just looking to quantify the I, you ask what is N in a state of N ordered AB equals P solutions. You can think of it as your universal time if you would like. How many frames of universal time, that's the quantity of I. And then the order quality within that defines various physical information. So the principle of efficient language states that for any ordered set of n state selections on the base possibility space, the universe computationally economizes total information as the sum of all E. E is explained in the code theoretic axiom article as a hierarchical set of compound symbolic meaning emerging from base symbols in any code or language. For example, a sequence of protein folding algorithms in the four-letter code of DNA would be built of bits, if you will, defined by some unknown quantum gravity theory. But the information content of the protein folding instructions would in no way be the sum of the physical bits. So we can't see much of this emergent information E around us, right? Because it's non-local, and we are local both in space and time. And even locally, we are incapable of measuring more than the faintest quantity of information in a complex system. The principle of efficient language axiom says the universal system does this for the purpose of making more emergent physical and other information with less base information. Computational economy creates more negentropic reality for a given quantity of computational actions. So why would the universe be interested in making the information of physical or other patterns over time economical as it does? Well, I'm not sure, but I think it does. And because it is a self-actualized or self-emergent system, it happens to make more of itself by doing so economically. So maybe it's for selfish reasons. So if that's an objective, in the axiom at least, with a little bit of physical evidence, then there is rationale for making physical patterns economically. The principle of efficient language is a good choice if you suppose nature is computing AB equals P solutions, or computing anything at the base of it all. And then you suppose that there is observational evidence that nature worries about economy, even if all you look to is sort of Feynman's conversion of the principle of least action to his sum over history's path integral approach. There's enough evidence of the idea that this is a safe axiom. But again, if you want to really get into this, look at John Numrich's paper. It's kind of seminal for this particular point. It combines fundamental physics equations with an abstract, relating to the principle of least action, with an abstract possibility space of all possible programs, codes, that could simulate something, such as a physical reality. And so Numrich uses very good logical rigor to show how the most economical program has the highest ontological probability to be what the system that supposedly computes is using as in the infinite space of possible programs. Anyway, let us now reapproach that question that I said was important. Remember, we said a clock is an ordered set of ordered sets wherein a repeating cycle of change occurs in such a manner that all objects in the set are changed over one cycle, one tick of the clock. So this definition of a quantum clock cycle allows two or more elements to change in a single frame, but we ask, should it? Put differently, for this pattern right here, do we need frame number 2 at all if we have already changed element 4 here in frame 1? That's the question. Well, the answer should be no, because the objective is to complete the cycle with no exceptions by changing all elements in each cycle with as few objects or computations as possible. It is not computationally economical or necessary for the pattern formation to waste a computation or action if the state selection number 1 changed element number 4. For example, if we were to play this for you at 24 frames per second, so we would just repeat this section of the film strip and literally project it at 24 frames per second. What you would see in the projection, if we played all 5 frames, is you would see a blurry kind of ring, and it would be pinkish like Ahmed's shirt. But the problem is here at element 4, at about 7 o'clock, okay, it would have a double darkness asymmetry at element number 4, because we're talking about the pattern and clocks of quasi-particles, which are kind of illusionary coherent patterns. And so that, unless we were trying to do that, but we're not trying to create a pattern in this invented case where we want a blurry ring with a double density of red points at 7 o'clock. So that's what I mean by saying it's not necessary for the particular pattern formation. It's a waste. So accordingly, if one frame changes more than one element in the base pattern in a single change step, that's okay. A computational savings occurs. It's more than okay. It's what will drive this entire physics. It's our energetic principle, which is converted to a computational least action principle. Okay. So now let's go to a few geometry facts and figures before we start building up into this quantum wave function and start arguing that table about the fundamental constants I showed earlier. So technically, quasi-particles, they come in many, many classes, right? Quantum dots, phonons. And in the quasicrystal formality and literature, they're called phasons. They're much more mathematically oriented than any other quasi-particle, because ordinary quasi-particles are based on physics, which is blurry, observation-based. Phasons, on the other hand, are very, very rigorously connected to the shift vector actions on hyperlattices, which generally correlate to Lie algebras. And we, really Phong, really for the first time ever created the rigorous and ultimate mathematical reduction to define language or syntactical freedom in quasicrystals by her realization that for any shift vector action, it is a selection between a finite quantity of relationships between something called the empire window and a boundary called the cut window. And you can you count those possible shift vector actions, which can be seen as algebraic actions in the abstract space, and you pick one, and there's a finite set. When you pick it, you create a change in your projective space between object 1, which is projection 1, and object 2 in the ordered set. In other words, how you pick your choices with the shift vector code related to Phong's empire and cut window, that is how you create the quality of the ordered set. So obviously, you need some sort of believable mechanism in your model that says, all right, so you've picked this projection in 1, so you get to the second projection in the ordered set. Why would you select one projection over the other? right? And so we're going to get into that. But, so you know where I'm going. It's the principle of least action. It's the principle of least computational action, which is subsumed by the principle of efficient language, which will force us into our set of choices that we can invent as to why one of Fang's shift vectors at some time 2 would be selected with higher probability over another. So due to empires, these quasi-particles are inherently non-local. And due to their origin as lattice transformations, they are naturally discretized in time and space. And due to the fact that all dynamic quasicrystals with their quasi-particles are themselves expressions of languages or codes, they are inherently non-deterministic. Because you cannot algorithmically predict the outcome of any language, whether spoken or an algebraic computer coding language, because a language itself is defined by a finite set of objects plus strict ordering rules plus syntactical freedom within the rules such that you can use C++ to create meaning in the code. Accordingly, any quantum gravity model that uses quasicrystal math would naturally be a non-local and non-deterministic hidden variables theory, which is not, therefore, in violation of Bell's theorem. So let us introduce our computational quantum energy principle in 2 dimensions first. A 1D dynamic quasicrystal has 1D quasiparticles defined as ordered sets of movements of the projection window in the higher dimensional space. When 2 phazon quasiparticle elements of 2 or more 1D quasicrystals are coincident in a 2D quasicrystal at some frame, there is an element savings in the quasiparticle pattern itself. For example, if we imagine a blue quasiparticle traveling from left to right and a red quasiparticle traveling from the bottom left to the top right, and where a coincident step in the 2 1D dynamic patterns exists here, well, then we save a computational frame without compromising the propagation of either of the 2 patterns. Since the universal frame count would be the same as if the savings did not occur, this can be interpreted as an acceleration of both particles, because your universal time is the same, but you've saved a frame, so it appears to accelerate. On the other hand, if 2 or more one-dimensional quasicrystals cross in a different manner, a computational savings is not realized, and there is null interaction, and there is no acceleration. The same phazon quasiparticle dynamic steps are expressed for each one without any computational economization here in this second case. The E8 lattice has 120 parallel line classes. Each infinite line is segmented by unit lengths defined by the cross points with other lines to form the root vector lattice. A randomly chosen angle will, in almost all cases, transform the 120 parallel classes of unit vectors of E8 into 120 non-zero lengths greater than 0 and less than 1. The special case comes when using the only angle that transforms the lattice slice into H3 or H4 symmetry. In this case, each vector is transformed into one of only 2 values in 4 dimensions, 1 and 1 over phi, and 7 Dirichlet integers in 3D and 1 transformed to 0 in 3D for 7 plus 1 equals 8 transformations. The special angle that creates the case of 2 transform lengths, 1 and 1 over phi, versus the infinite set of projection angles generating 120 transformation lengths is from trivectors in E8. It's from the relationship between two or more trivectors in E8. Specifically, the fundamental angle from which all angles of the hypervector projection angle are derived is the trivector rotor, okay, which transforms one 3-simplex onto a face-kissing adjacent 3-simplex, which is in a different three-dimensional subspace, composed, where both of them, of course, are simply composed of the E8 root vectors. And that angle, to make that rotor transformation, is irrational, arc cosine 1/4, which happens to be a fundamental angle, which is the arc cosine of 3 times phi minus 1 divided by 4, which is about 15.5 degrees, plus arc cosine 1/2, 60 degrees. And we call this irrational transformation the A coefficient. It acts upon the B coefficients, which are the 2-simplex angles in the E8 root lattice with the value arc cosine 1/2 and multiples thereof. And A times B equals P, where P is the product expressed as geometric lengths, as Dirichlet integers, quaternionic values as the icosions, matrix values correlated to Coxeter's H4 folding matrix, and various other matrix formalisms and other formalisms. In 4D, the AB equals P projections generate a network of Fibonacci chains that composite into 600 cells that relate as 7 Dirichlet integer overlaps and 1 kiss at an overlap distance 0. The 7 plus 1 relationships between 600 cells in the Elser-Sloan quasicrystal are ordered via rules and syntactical freedom to form a geometric and an algebraic code. So the Elser-Sloan quasicrystal is dynamic and has quasiparticles. A shift vector random walk code in the E8 lattice animates the code in the Elser-Sloan's Elser and Sloan's quasicrystal to form phazon-based quasiparticles in 4 dimensions. There are no physics in a single frame or AB equals P solution. All physical information is relationship, and this requires an ordered set of 2 or more AB equals P solutions. The Cartesian coordinates of the 120 vertices of each 600 cell in this dynamic Elser-Sloan quasicrystal are equal to the analog of our 20 group. In 4 dimensions, it's 4D is the compound. In 4D,
no, it is the 4D. You're referring
yeah,
to
thanks. I was looking for the missing word. It is the 4D. It is the 4D. It is the 4D compound of 5 D4 root vector polytopes. So if you just take the D4 root vector polytopes, right, which is a 24 cell, and you compound them in the only really symmetric or logical way to do that, where they share a common centroid, and that happens to be the angle that we use for our whole physics program, which is this special rotational angle based on the A coefficient, which acts on the E8 bivector angles, and also is the way that we create the QSN. It's the same angle. In our case, we have to cast out the arc cosine 1/2 component because we don't have room for that in 3D. So I call that the trivial component of the angle. So arc cosine 1/4 minus arc cosine 1/2 is 3 times the golden ratio minus 1/4, and the arc cosine of that. So this is 524 cells, which describes the Cartesian coordinates when they're compounded with that angle of the 600 cell. So this is the analog of our special object in the QSN here, where we take a cube octahedron, which can be, this and this have the same convex hull, same Cartesian coordinates of the outside of the vertices. So, and we rotate that guy. So if you rotate the cube octahedron, the root vector polytope, you get these Cartesian coordinates with these kind of connections. And if you rotate this version of the same 12 vertices, you get this object here, which has the exact same Cartesian coordinates for its points. There are 60 points. So each cube octahedron is equal to the convex hull of the projection of one of the 524 cells of the 600 cells in the Elser-Sloan quasicrystal. In other words, if you were to just take one 600 cell and recognize its 24 cell compound, and you project one of the 24 cells orthogonally to R3, then you will generate exactly the convex hull of the root vector polytope of D3 equals A3, right? So accordingly, the 20 group maps 24 5-cell compounds in the E8 to 4D transformations. It maps to those. So by preserving local particle scale A1, A2, and A3 symmetry within our overall 20 group, which is H3 symmetric, we might be able to better exploit known group theoretic particle physics because of how these objects here correlate to SO1 and the necessary fundamental group theoretic objects that clearly relate to nature. The E8 lattice can be built as a periodic packing of 3 simplices in R8. So if you just wanted to build the E8 lattice and all you had was one tetrahedron, you could just copy it and rotate copies into other spatial dimensions and build the entire E8 lattice with just that one building block. But that object that you would build, this E8 lattice, has absolutely no notion of braids or right and left helices or any such things. The lattice is also not a language or a code. We have something called tiling languages. So quasicrystals are a tiling language, and it is distinctly not a tiling code. Upon projections of various random walks of the shift vector operator code in E8, the AB equals P solutions are always helical paths of the same tetrahedra that were formerly, in their former life, members of the E8 lattice slice, but they got rearranged in R4 to form various helical paths like this in the Elser-Sloan quasicrystal. So it gets kind of curvy and twisty, and a new sign value comes into the projective space, right or left. So you have a helicity value as well. Because all the tetrahedral edges in E8 get equally transformed to 1 over square root via the A coefficient angle, the smaller tetrahedra in the Elser-Sloan quasicrystal are regular. They're 3 simplices. So they're just smaller by 1 over square root 2. And that's important to us. We like 3 simplices for some reasonable reasons. Each helix made of tetrahedra in the Elser-Sloan quasicrystal is a 3-braid of discretized 1D paths. It's actually not a 3-braid. Well, when I say 3-braid, what I mean is it's a braid of 3 different one-dimensional paths. I don't mean it's a 3-dimensional braid. So, right, so this is basically, if you follow the surface here of each one-dimensional closed path, you'd find that there are 3 of them. And in fact, the 3 are regular decagons. So if you took a regular decagon, if you wanted to reproduce this convex hull, you would take a decagon and rotate it upon its centroid by arc cosine 1/2, 60 degrees into the 4th spatial dimension. Then you take another one and rotate it also upon the rotational center, or the center of the decagon, and rotate that by arc cosine 1/4 into the fourth spatial dimension. And now you have 3 decagons sharing the same centroid, but which the group of 3 live in 4D, and describe the convex hull of the projection of a bunch of regular 3 simplexes in E8 down to R4. And this pattern here has 2 types of periodicity. It has 3 periodicity and it has 5 periodicity, and it's a little bit beyond the scope of the time we have to explain why. But you may be interested in the 3 periodicity in the same way Garrett is for the electroweak modeling, where Garrett, is interested in the idea that there's some unknown 4-dimensional polytope which has an unknown 4-dimensional torus. This is kind of like a torus in some vague sense, and where a particle rotates in Garrett's, if you just go to Ted Maui, Garrett Lisi, he does this little 20 short TED talk. Anyway, so Garrett sees this polytope so Garrett thinks it's not a 3-sphere, it's a polytope in 4 dimensions. It has on it a 4-dimensional torus that has something for some reason to do with 3 periodicity, and then something rotates on that in the abstract space, and points or objects pop in and out of the projective space to give you evidence, observational evidence of something relating to 3 periodicity, right, in the electroweak model. And so I think for us, if we got interested in Garrett's rationale, we might start speculating here that maybe, because all of the movements in the QSN deeply relate to the natural patterns of flow and helicity in these 7+1 600-cell relationships, which can be reduced to 24-cell relationships in the dynamic Elser-Sloan quasicrystal. Anyway, we have 2 important objects. We have many important objects, but there are 2 here that I wanted to talk about. So the first is the quasicrystalline spin network, or QSN. We can think of that as a possibility space, but we're going to have to modify that in the way we've been thinking about it, and Fong and I have recently agreed, and her and I have both thought for quite a while anyway, but we just yesterday had a verbal confirmation. We're going to have to rethink the QSN and allow an infinity of possible deflations on it. So we have to get a little bit more abstract mathematically. It's still going to be the QSN, but it will allow an infinity of deflations upon it. And that's all very rigorously explainable, but not now. The second object is the subset called the compound, or the compound quasicrystal. We call it the CQC. So by using Fong's relationships between the projection or cut window and the empire window to move, and don't worry, I don't even want to say this word projection window. You don't have to use the cut window to be your projector. You can project, if you want, just the empire window. But the salient point is the relationship between the cut window, which is larger, and the smaller empire window. So anyway, by using the rigorous relationships that she defined for quasicrystal syntactical freedom to move the subset of this CQC around some finite boundary within the QSN, we create phazon quasiparticle dynamics. I think that's unclear. This infinitely deflatable QSN, which is an infinite object, you start in the thought experiment to understand this by taking some finite subset of that, a box. And around that box, within that box, you can relocate the rotational center. So in other words, the infinite one has one and only one rotational center. Now, let us take the infinite one and arbitrarily place a a three-dimensional box. Or not arbitrarily, we can put the rotational center at the centroid of this box. Now, we may create AB equals P actions in the hyperspace that move the rotational center around to different coordinates, XYZ coordinates within the box. And by ordering those movements over T in an ordered set of XYZ T's, then you create animations, quasi-particle animations. An interesting code-theoretic way to think about these objects is to let me show you an analogy of bits to bytes. The fundamental bits are the two letters or one simplex lengths, 1 and 1 over the golden ratio. The QSN and the Elsner-Sloan quasicrystal can be built solely from these two letters. In code theory, we start with an irreducible set of letters, and then we go up ad infinitum from there through words, sentences, and so on. In binary code, the letters are bits and the words are bytes, and then it keeps going up from there to about 10 levels of compound hierarchical symbols to encode your favorite DVD movie. Coincidentally, one can think about how the Fibonacci chains defining the Elsner-Sloan quasicrystal combine to form 8 one-dimensional relationships as 7 lines and a zero simplex, a point, defining the 8 distances of relationship between 600 cells. So this is what they look like in the Elsner-Sloan. They relate to each other with a kiss. That looks like it's overlapping, but it's just the angle. They kiss. They overlap a little more, and so they get to this. So each of those overlaps is a distance. So the two bits or letters, 1 and 1 over phi, composite. And the values in the composite, these other one-dimensional lengths, are there are 8 of those. So you have to arrange your bits correctly in order to get these bytes, or any of these 8 different sort of emergent lengths. So let's talk about the wave function idea. This 20 group here at time 0 is the origin of a radial empire of other 20 groups. It is an emperor, in a sense, with 30 empire rays as Fibonacci chains of 20 groups, running outward to infinity and dropping in density as 1 over r squared. We're going to build a toy fermionic clock together. If there are 20 groups in clocks in the advanced and retarded directions of time on the particle's path or world line, well, then we save steps of change for the expression of the overall pilot wave function. Remember, we've carefully defined a quantum clock, and it allows for more than one position to be satisfied in a propagating clock cycle in each AB equals P solution or frame in the ordered set of sets. The principle of efficient language axiom is our energetic principle, which equals a computational economy principle. So, when multiple positions in a clock's forward or backwards in time positions, or within the same clock position, are on due to empire rays of these 20 groups, which are distributed in Fibonacci chains that radiate outwards, then these positions are not repeated, and large numbers of AB equals P solutions are saved. The greater the constant rate of savings per clock cycle, the greater the fermionic particle's mass. That is, the more it saves, the more it can lose when it starts a new world line in a different direction, an inertial frame of reference. Later in the day, I will really do better to defend this, how when it changes, it loses its constant rate of 20 group savings. It loses its constant computational savings, and that's going to cost you something physically. It'll create inertia. So our model predicts that any observer will measure the speed of light with the same magnitude. But, and I'll show you why, but it rejects the philosophy that there is no absolute motion or absolute notion that it rejects the idea that there's no absolute motion and there's no absolute time. And by the way, the only reason to accept the notion of relativity, that there ontologically can be no absolute motion or time, is only if you accept the philosophy or the conjecture that space-time is smooth. Because if it's not smooth, then one can move relative to the background, relative to some modern discretized ether. Instead, particles have an intrinsic but changing absolute ratio of internal clock steps relative to forward propagation steps. For example, if we have 100 AB equals P solutions or frames in our quasi-particle animation, well then we can have various integer ratios of contribution toward internal clock time versus forward propagation. But it's a trade-off, right? So if you go up on one, you go down on the other. So we have several options to explore for clock cycles in the QSN. And it should be decided based solely on the principle of efficient language, which means the internal clock quasi-particles that we select must have the greatest 20-group savings. That's the only thing we should care about. Consider the red circle here to be our emperor. It has 30 Fibonacci rays of 20 groups coming out from it. Each 20-group ray is a microscopic, or each 20 group, right, in a ray, you should think of as a microscopic potential. So it's a microscopic energy well, if you will, that lasts for one Planck moment or frame. The PEL guides the statistics to save AB equals P solutions. So the probability of a clock changing its direction and its ratio of clock time steps to propagation steps, which we call the TP ratio, is based on where the 20-group quanta of gravity are and will be, which is the quantum gravitational energy landscape. That will be our statistics. That is our energy landscape. The network of 20 groups over some ordered set of clock cycles defines a discretized quantum field theoretic energy landscape in the 3D shell model, which I should call the Piero Truini cosmology, because he triggered me to think it through over a year and a half ago. Tensor networks and the order parameter. Each Fibonacci chain of 20 groups rigorously maps to a string of zeros and ones, which is called a Fibonacci word. Each Fibonacci word in each moment maps to a Fourier representation that is a fractal with a unique fractal dimensionality measure. These different representations are different syntactically legal permutations of a Fibonacci chain of the same length. In other words, go back up to Fang's relationship choices between the empire window and the cut window. Each one of those choices that she has, let's say she has 5, because we set it at 5. So each one of those 5 will create a different Fourier representation with a different magnitude or signature of complexity, which can be measured by various analytical methods. So these are all from the same length Fibonacci chain. So this is a thing that you would see is say, okay, I see it, and then we have Fang up in the hyperspace change the, well, it's not the hyperspace. If it's 1D, she'd be working in Z2. So she'd just be in the Z2 space. You'd be looking at this change, you'd be like, well, it looks basically the same. I see a phazon flip here in the 1D chain, but they're all basically the same. Why would one create a Fourier representation that looks so different, radically different than the other, and what's the physical significance of that? Look at this. This is very diffused, right? And this is different. And look at this complexity. These are chains, very long chains that have the same length. They're just different legal expressions of the code, which are different relationships of these shift vector actions in this finite set. These objects don't just have a unique fractal dimension value. They actually are fractals in the technical sense. And each can be generated via a non-deterministic iterative output algorithm sequence, which is called the OA to OB parameter quadratic iterative function. And I don't know what it is. I just know what I'm calling it and that we have to find it. I have been hand-waving and I've been vague with you this morning about how exactly the principle of efficient language compels the negentropic quality of the increasing order quality. Remember, all our physics is nothing but the quality of order within an ordered set. And so I haven't told you anything about how in the world the principle of efficient language can govern this shift vector code in E8, which generates these ordered sets of AB equals P solutions. It is beyond the scope of our time today to give you details, a lot of details, on my thoughts of possible forms of the OA to OB parameter quadratic function. But I will say that OA is a signature of complex systems order in the physical space, which maps to a bijective measure, OB, in the abstract higher dimensional AB equals P solution space, which is the quantum energy landscape, to define probability amplitudes for some time too, that you're going to ask the formalism about. The picture that I am painting is a sum over histories path integral approach in the vast possibility space of AB equals P solutions. And I will do better to clarify this. For now, let us continue with the Fibonacci chain quasicrystals, which become these strings of zeros and ones called Fibonacci words. Under Fourier mapping, some contain the cardioid form in the Mandelbrot set. I showed you all those other pictures. This is one of them. Again, you could take the diffused one and you'd look at that Fibonacci chain, you'd say, they look the same basically, just a little different, and what's the difference with these shift vector actions? Why so different? So under Fourier mapping, some contain this. Many patterns in nature recreate this cardioid shape, okay? The coincidence, though, is that this cardioid shape is created by a fractal. This is a fractal, and we published why that is. Other cardioid shapes in nature, like in mechanics, they're not fractals. So it's interesting. And perhaps even more interesting, our golden ratio-based fractals have something in common with the quadratic iterative function that is the Mandelbrot set function. The Mandelbrot set encodes the golden ratio and the entire Fibonacci sequence. And my understanding is that no one knows why. We can get anybody references on that, but it's in the ratios of the bulbs as you keep going, zooming in and out of this infinite Mandelbrot set. The ratios of the bulbs follows the Fibonacci sequence, and the Fibonacci sequence defines the golden ratio at its limit, so it's very weird. And I don't think anyone knows why. So you can imagine why I'm interested in multifractal, not fractional, multifractal dimensional analyses as one candidate for our OA parameter. Note how some Fibonacci chains map to highly complex patterns with more emergent information than others. So there's something called wavelet analysis, which allows you to measure the complexity in a set of n points. So you can have a set of n points of, say, a million points in some boundary, and they will have different magnitudes of complexity as measured via wavelet analysis. And my interest in total information is not to count the points. My interest is to count the points and the emergent information. anyway, all of these would have different magnitudes under wavelet analysis and a few other various analytical ways to measure complexity and emergent pattern. Again, these differences in richness are not related to the length of the Fibonacci chain. Each of these is a single frozen moment or frame for just one dynamic Fibonacci chain. Both the Elsner-Sloan and the QSN are dynamic. They are ordered sets of AB equals P solutions wherein order quality is defined by our energetic equals computational economy principle, and where each member of the ordered set is a relationship between Fang's empire and cut window. At the most irreducible level, a quasi-particle is a network of changing Fibonacci chains, a string of changing integers where each influences or restricts the degrees of freedom of the other changing integers in a co-evolutionary manner throughout the entire network. And when you get to collective excitations or you get to neural network theory, you get emergent patterns that can loop back to influence the evolution of the system. And these are very important for physical formalism that is reductive and kind of first principles as what we're trying to achieve here. So you can think about this numerically if you want, because each animation of a 1D chain is an ordered set of large integers which are called Lucas numbers. Each dynamic Fibonacci chain maps to an animation of these two-dimensional Fourier representations. Each one-dimensional chain in the physical space that maps to a 2D representation in this form of Fourier plot map animations is equivalent to an ordered set of matrix code operations. We can get out of geometry, okay? And each of those participates in an interactive system of matrices, a tensor network code of quasi-particles and discretized space-time. Any small region of physical space-time and particles contains a Fourier domain-based multifractal signature. That is the OA parameter that one of you must find for us, or we will not be able to get very far with our program here. Because we can't compute in geometry. We can't do simulations with ordered sets of projective transformations. Impossible. Maybe in the future when quantum computers exist, you could do that geometrically. Not us, not now. Again, the OA parameter maps as an iterative input value to the OB parameter, evolving the random walk probability amplitude possibility space of AB equals P solutions in E8. A little bit more on the quantum wave function. Let us go into a little detail on the quantum wave function and connect that with some of our earlier discussed ideas. First, let us say that a clock-based particle like ours is an ordered set forming a repeating pattern that cycles a three-dimensional clock. The pattern is an ordered set defined by the order of AB equals P solutions, which again is going to come back to the mathematics of the empire to cut window relationship. The random walks are energetically probable paths from the sum of all possible paths, each statistically weighted by computational economy considerations in the possibility space of AB equals P solutions. When I show the red circle like this in the animation with the black around it, well, that means, when I just show the red dot, that means that's where you should visualize the emperor, okay? So the emperor is the one and only one object that lives at the center of the empire window in the abstract space. So when we have an emperor in the P solution space, the physical space, that means that we have its counterparticle or its other, what did Richard say yesterday? His costume was his alter ego. So you have its alter ego, its alter ego in its different form lives in the hyperspace, and there it lives uniquely at the exact center of the empire window. Or it lives at the center of the projection window, because again, you can project the empire window, or you can project the cut window. You're looking for relationships between the two. All right, now when an emperor is like here, okay, there may be empire 20 groups in places that are not here, like here, okay? Or there could be one out here that's not even in the same clock. So that one's in the same clock. This one's in a different clock, forward in the future. So when you see this symbol in the animation, it means an empire 20 group is there in that frame or was there from another frame. So it is a frame savings and does not need to be repeated according to the argument we built up. Boom, our first frame savings. Another, another, another. We completed the cycle. Notice that we had two-letter quasicrystal spacing along lines here. A small network of Fibonacci chains, long, short, long. This allowed the 10 steps we would have needed for our clock to be completed if we had answered oppositely an hour ago when we kind of deduced why this definition of a quantum clock should not require the repeating, and talking about Ahmed's red dot at 7 o'clock, right? That whole discussion. So if we had answered differently at that point, we would have needed 10 steps to create the meaning of this pattern, this cycle. And so in this case, we have saved 5 frames. We got more done with less. If we had spacing that was deflated or inflated or ordered differently, we would not have enjoyed the same maximal rate of 20 group savings, because I could create a pattern for you that saves a lot, or I could deliberately create a pattern that saves less. We have an enormous number of choices of the relationship between the empire window to the cut window. I mean, very, very, very large numbers, like 10 to the 500. They're just very, very big numbers. And you can understand really simple in geometry, for geometric reasons, why that number is so exponentially large. Anyway, everything in quasicrystal physics is about the ordering of our sets. For example, let us take a Penrose tiling that has tiles that are this big and that is on a plane that's this big. So it's just a 1 square foot space and the big tiles are 1 inch. There's not very many possibilities of how we can follow the syntactical freedom to create different tilings. Each one of the tilings is related to a different Phong relationship of the empire to cut window, okay? So think about Phong up there for fun. And so she's in the hyperspace of Z5, which is a generator of the Penrose tiling. And Phong is up there, and we're all down here. And she's like talking to us on the phone. And she's only got 10 choices, 10 AB equals P solutions that she can possibly do. So how many ways, how many animations can those of us in the room create with her 10 possible shift vector relationships? Well, the answer would be 3.6 million, because it's 10 factorial. So it's really interesting how big this physical path integral formalism space is. The superposition of all walks is enormous, right? The name of our game is to spike the probabilities. We want to attach probability amplitudes to this massive space of probabilities, of possibilities. So anyway, let's say that there are these 10 legal ways to order the tiles that correspond to 10 empire cut window relationships to the projection window relationship in the Z5 lattice, up there where Phong is, on this very small patch that we have to play with. So these 3.6 million ways that we can create animations of the 10. So it's known that Navier-Stokes equations model observed phazon quasiparticle patterns generally in 3 dimensions. Equally as well is the very abstract cut plus projection method. So when you think about this idea of the empire window to projection window, it's, although that is super novel and foundational, the general idea of modeling physically realistic phazon quasiparticles in H3 symmetric quasicrystals in 3D is studied by just moving the cut window through the hyperlattice space. And there you get the predictions of how the quasiparticles behave. But if you don't want to use that formalism, if it's too abstract, and you want to use Navier-Stokes equations, you get the same quality of prediction of how the quasiparticles will behave, which is interesting. It's interesting to Marc Debassou, who's one of probably the top 6 gurus in the quasicrystal space, you know, at the conferences. He finds it interesting that such radically different formalisms, the Navier-Stokes classic versus this really mathy, higher dimensional way, they somehow are converging to the same solutions. All right. With this being true, one can think of a dynamic quasicrystal as a discretized fluid. And the 3.6 million ordered sets that we could create with our 10 Penrose tilings that are very small, which Phong has gifted us with from 5 dimensions, all of these, each ordered animation, is just some expression of this discretized fluid. Many, probably most, being noisy, worthless turbulence, and some being interesting patterns with just 1 quasiparticle, and a smaller set being interesting patterns with 2 quasiparticles, and so on. This is the case with making clock patterns of 20 groups from some finite set of AB equals P solutions with some order parameter iterative function. So remember, the job of this guy is to assess probability amplitudes. So that OA to OB parameter influences the shift vector random walk code up in E8 to order our ordered sets. So Navier-Stokes equations in a discretized form are more than just a metaphor for us. Information theoretically, a turbulent fluid phase wastes actions. It wastes energy if you want to create emergent pattern or information in that fluid. Kinetic energy in a turbulent system reduces due to particle collisions, which generally cause decelerations. The energy is then generally shifted towards useless free photonic radiation as the collision events cause photons to radiate as electrons change their electron orbital radii. And then that photon radiation further increases parallel vector classes in a Boltzmann's entropic sense, and that creates a cascade toward higher entropy or noise. Emergent information in this case decreases as noise increases, and for us, 20 group savings decreases as entropy increases. Less physical quasiparticle pattern for a given quantity of AB equals P solutions. When it gets noisy, you get less emergent quasi-particle pattern, in other words. So as the quantity of parallel vector classes increases to a sufficiently high value, then eventually no meaningful or long duration quasi-particle pattern forms in the fluid at all. When phase, entanglement, parallel vector classes, relative direction angle, and magnetic moment angle, etc., are all, let us say, coherently correlated, right, in some manner, like where I'm generalizing this notion of coherence. Or let's just say highly correlated. Then entropy goes down, kinetic energy goes up, right, because wasted photonic energy is going down and the conserved energy is transferred generally to kinetic energy. And also emergent structure within the fluid occurs. For example, in the kitchen, you've all seen that vortex, right? So if you use Boltzmann's entropy, where the W value is correlated to the quantity of parallel vector classes, then trivially you can see that these countless trillions of particles have an exponentially reduced set of parallel vector classes relative to the same system at the same energy that is turbulent, right? And what we have is the emergent structure of the vortex itself. You have more pattern and interesting things than in an ideally chaotic or a highly chaotic state of the same energy. So the point is that energy can be used for order or it can be used for disorder, because that vortex is having energy pumped into it, right? But the way that the energy is being pumped into my water vortex is reducing entropy. But I could pump the same amount of energy and increase entropy. So our task will be to deliberately rank the ordered sets that maximize missed opportunity for 20 group savings, and then, contrarily, rank other ordered sets that minimize lost savings so that we can discover the ideal ordered sets for our given clock particles in the pursuit of maximal 20 group savings. So let us talk about this wave function that has recently been realized and why it is a wave function. This is our wave function calculated. But it's a wave function of one of many possible clocks. So we made a clock that we're restricted on how we can make clocks in the QSN. So we picked one of the ways that we can make a clock in the QSN. We calculated a wave function.
Is that the square of the wave function or the wave function?
It's a square. It's a probability density.
Ah, okay.
So it's a probability density that if you were to randomly measure, yeah. So note that we do not know the pattern of our 3 generations of clocks. There are various choices, and we're looking for ones that have maximal 20 group savings. So let us recall the idea that clocks are just ordered sets of ordered sets. And remember that a position must be covered only once per cycle, even if it is out of order in space, time, and internal clock space-time. By the former logic, this extends not just to 20 groups in the clock that one is focused on, but it also extends to any clocks in the advanced or retarded, in other words, the forward and backward in time positions of this pilot wave and associated Schrödinger wave function. In real life, this type of mass or clock-based particle would always have some non-zero p in its T over p ratio, right? Where we assume that there is a background, a substructure, then it would be highly unlikely that any electron in a finite universe like ours is literally at rest relative to the background. So therefore, everyone would have a true intrinsic and changing T over p ratio with non-zero p. Accordingly, the clock and the very position of the particle as a pilot wave is always smeared out along its world line forward and backward in time. That is, its 20 groups are spread out across 1, the internal clock, 2, the advanced and retarded clocks, and 3, the space along its random walk or world line path. It is not made of a single 20 group changing positions. That is not the way to think about these quantum clocks of ours. It is non-local, and it is made of many 20 groups changing positions in computationally ideal ordered sets. The object itself is distinctly non-local in internal time, universal time, and space. It is more of a statistical blur that is made of quanta of gravity, as I define each 20 group as a quantum potential. So, if a particle clock position is here, here, and here, and if 20 group savings drops off because of the 1 over r squared nature of the empire rays of 20 groups to form an elliptical type Gaussian distribution of position coordinates, then where is the clock? Where is this electron? Where would Fong be if she were this electron? Well, she would be distributed over a set of positions simultaneously within this propagating bubble, the Gaussian distribution. But statistically, she would be more here than here. Her bubble would propagate classically, approximately classically, but her position within the bubble would be uncertain. So the bubble is special. The Gaussian distribution is special. In fact, even in principle, below this wavelength, there would not be a single position of Fong in a single frame. It would be a false question to even ask. However, taking the whole wavelength of this uncertainty bubble, this elliptical form, you could make a statement about the position and momentum of the sum of her various uncertain positions within her Compton wavelength. That would be reasonable. Our toy model offers this first principles explanation for the Compton wavelength, Heisenberg's uncertainty principle, and superposition. The images we made are for illustrative purposes only. The actual clock is not like this. The Compton wavelength is much, much larger, but you get the idea. And the 20 group savings extends further out in the advanced and retarded directions of its world line in a realistic version that we will find. So that's going to be one of the constraints of our clock search. We need to find a clock search that reproduces the Compton wavelength. Heisenberg thought that space and time were quantized because measurement data fit only into the discrete blocks of space-time corresponding to his matrix formalism. Digital physics and pixelated video monitors were not yet popular, so the smooth space-time ontology of Schrödinger and Einstein easily won the day. It would take another 50 years before Rovelli, Ashtekar, and Smolin would put some attention on the world scene onto Heisenberg's old idea of pixelated space-time. I don't think, though, that their approach will work because it is not code theoretic, it is too smooth, it has infinities. That, for example, they allow an infinity of deficit angle values or curvature values in their spin foam. And they have no hope of recovering first principles Lie algebraic gauge symmetry particle physics without forcing it in with plugs. But nonetheless, they are heroes of mine because they laid down some foundational groundwork for us. For example, like them, we use graph theory. And they showed that realistic approximations of Einstein field equations correlated to quantum mechanics can be derived from pure graph theory. So we look less crazy. We let them do it first, right? We started 10 years ago, and it's only now clear to me what our waveform is. So at least for me, this is a seminal kind of conceptual milestone. This pilot wave and wave function are similar to the idea of the Wheeler-Feynman handshake, where the energy landscape determining probabilities for position measurements of 20 groups is an integration of the advanced and retarded in time positions of the particle clock's world line at some constant t over p. We sum the quantity of AB equals P frame savings within the clock itself at time 0 and at t plus minus 1, t plus minus 2, and so on, to generate a constant and ideal rate of frame savings, or 20 group positions, within our pilot wave function. The Gaussian distribution of the wave function of 20 group savings drops rapidly both forward and backwards in its world line to form the Compton wavelength. The PEL requires that the statistical probability allowed within the rules of the random walk code in E8 generate high probability amplitudes for measuring a 20 group at XYZ t coordinates that will save AB equals P solutions. 20 group distribution in our model of the universe is exponentially denser than the observed density of particles. Accordingly, the vast majority of our particles at any moment will be analogous to the dense distribution of particles in the Dirac sea or to the density of Higgs particles. But we should not try too hard to connect our ideas yet to other models like this, of course. For now, we're following our two axioms in the particular manner we are inspired to via E8-based quasicrystal math and my code-theoretic computational ideas. What I can say with confidence, though, now, is that this toy model states that each position of a 20 group, whether part of the background or participating in a particle pattern, is a quantum potential that I don't mind calling a quantum of gravity, as long as we in the room can agree that everything else must be built from this quantum of gravity. Why then is there exponentially higher probability for measuring a 20 group along the world line of one of our clock particles than in vacuum, if it is true that 20 groups are so densely spaced, right? Because the probability for measuring a particle around the discretized field of 20 groups from other particles nearby it, or even its own electron self-interaction, it's just exponentially higher than the probability that it will be at some time too at these imagined gravitational potential, or these energy potentials in this dense array of 20 groups that are everywhere. Well, for one thing, these empire waves or pilot waves are not 20 groups. They are gigantic clouds of 20 groups over time, some mapped as XYZTs serving one position, some serving the position of particles and 20 group needs in the clock patterns, and some 3, some 4, etc. In other words, the quality of the ordered sets defining one of our discretized pilot waves is coherent with periodic clock cycle and aperiodic spatial propagation patterns. In other words, there will be more 20 group savings along the pilot wave world line, but exponentially more. And I'll show more later about, I'll try to make it more clear to you about exactly how big the delta can be between densities of probability for 20 group savings. Anyway, according to the principle of efficient language, this will increase the probability densities of the AB equals P solutions that correlate to these positions so that fundamental particles, to the positions of the self-interaction positions, such that with the computational efficiency pattern, you will find persisting quasi-particles. They will persist unless strongly interacted. And remember, interaction must be more 20 group savings. So if I'm enjoying my own electron self-interaction, I'm like a Pac-Man eating computational savings. I'm just loving life, right? The only way you can get me off that, according to the computational economization principle, is you have to offer me more. You've got to offer me more than what I'm getting. Then you can get me off that path. And for another thing, the 20 groups are not always spaced densely in time. This is a crucial idea that I will explain after lunch when we talk about general relativity at the end of our time together today. This is really important. The density over time in the shell model of where energy potentials can be is about as great as the distance between 1 and 10 to the 44, the Planck time. So this model, though, predicts something radical. The quantity of fundamental particles in the universe increases over time. Why? Because all particles are ordered sets from a possibility space of incredibly, which is an incredibly large set of ordered sets. I find it amusing that you can arrange 16 equal-sized patches or configurations of a Penrose tiling 22 trillion ways. 16 factorial. So if you consider 10 to the 44 an animation, right, at a frame rate of 10 to the 44 per second in 1 cubic millimeter of vacuum space, well, then there would be 10 to the 44 factorial legal physical patterns that can be created. That may be technically incorrect, but the point is that there are enormous ways that you can order things, most of them creating no particles. And so I suggest that we're living in a universe where the quality of the order is increasing, where I imagine the OA to OB parameter as insignificant at 2 Planck moments after the Big Bang. And I imagine no quasi-particles at that time. Now, statistically speaking, with 10 to the 44 frames a second, there's going to be an accidental blip of order that occurs just with some probability after so many Planck moments of the action horizon shell model expansion. And once that starts, once a clock pattern forms, then the OA parameter is giving you a signature of order, okay, something less than ideal noise. And that signature of order maps to the OB parameter, which somehow has to plug in to the dehomogenization of the probability amplitudes on how this algebraic actions of the shift vector language or code in E8 behaves. And once that starts, you in some sense are in a negentropic universe where all of these patterns, where once computational economization starts as a seed, it self-organizes other things. It keeps influencing in an iterative evolution this input-output function that is the OA to OB parameter cycle.
Klee, you found a good spot to stop, maybe?
Yeah. So we'll stop in like 2 minutes. Okay. So anyway, this statement is false, as I told you a few minutes ago, and my next slide says that it's false. So there are greater than 10 to the 44 animations possible. And that is because each shift vector action at each frame has a very large set of n relationships to select from between the empire and projection window, that is, their relationships, unless we do a model where the ordered sets are only from the combinatorics available within the set n. So you could just keep taking set n and using its possible set of empire to projection window relationships, but that's not what the shell model says. Shell model says that as we go out and the universe increases in radius, this global projection operator that layers these shells of expanding reality, each has a very large and increasing n. But n increases infinitesimally small to the same extent that if you take the surface area of a sphere of radius 1 relative to the surface of a sphere of radius 2, there's a very large delta. But if you take the surface area of a sphere of radius 1 million and 1,000,001, then of course the surface area delta is trivially small. And so how large are the sets of relationships between the Empire window and the projection window? They're outrageously large. I don't know, but I think you should think in the realm of very large numbers, like 10 to the 500. It's really big, and it's easy to demonstrate why Fong and others could do that.